Okay, so in some sense, this is the last lecture. Uh, I was going to ask you guys at the end, but at the moment, all I have planned for next week is just some review problems, unless you guys want to do something for fun. But my goal is not to introduce anything that would appear on the exam next week. We don't have any more homeworks going on, stuff like that. So the class is basically wrapping up. Um, okay, so I wanted to, uh, so yeah, roughly this last segment of class, again, was about average in two different senses of the word average, amortized analysis and randomized algorithms. We did a week on randomized or amortized, and then we did 3 straight lectures on amortized, including hash tables last time. And then I wanted to throw in one more uh, data structure lecture just to kind of as an extended practice of amortized. Um, maybe just an example of some of the kind of creative things people do uh, that will take full advantage of this definition. Um, okay, so yeah, just as I guess that collage of our amortized lecture several weeks ago. But that first starting example, was like binary counters. Why are binary counters, generally efficient, even though they can flip many bits? It's because they're still flipping a constant number of bits on average. Uh, Other examples I think included like array lists and the doubling trick, or binary search trees as lazy rebuilding, or 2 stacks make a queue. And there's different ways to do the analysis. 2 methods besides the direct one include some kind of credit scheme where you're sort of, in a sense, paying for future work, but trying to figure out how to charge it to past operations. An alternative might be the potential method, uh, which is sort of similar, but somehow is that payment is often closely tied to some structural properties of your data structure. It seems like some cases are better suited for others, but really they're both just metaphors to facilitate your analysis. Um, okay, so that's amortized stuff. Um, so what I have prepared today is a bunch of stuff based on sort of advanced extensions of binary search trees and kind of creative things you could do with them. Um, uh, so let me introduce it by first just talking about a few applications of increasing sophistication. So one is kind of general setting is, you're given a bunch of sort of points on a line. Your vertices are alphabetically ordered, or your points are alphabetically ordered, or they represent some numerical value on the line, right? So they're keys, and they're ordered. And let's say that all your keys are also associated with weights. And so the query is, okay, what is the sum of weights between point A and point B, right? And the point is, we want to be able to do this very quickly, kind of respond to a query very quickly, and we want to keep responding to queries as we add or remove points from our data set. It's a basic problem. You guys probably already know how to do this. Here's a sort of a similar problem, but has, a little more sophisticated maybe. So rather than associating each point with a value, maybe each point is associated with a list of values, which might be empty. Okay, and you might ask, can you give me all the lists combined between points and points B, points A and points B, point A and point B? And we'll get there, but what makes this problem a little bit trickier is it's not reflected in this picture, but maybe many of those points are empty lists. Okay, and at some level, your query should be able to sort of bypass all the points that are empty. You don't want to have to visit all these things just to find out it's empty. You want your running time to maybe be proportional to the combined size of the output list, which may skip many of these points. Okay, so that would be maybe a little bit trickier than the last sum of weights. Okay, so those are the first two kinds. Now this next kind of application that I think we'll discuss is a little bit different. It's not going to be solved directly by search trees, but I'll explain that when we get there. But so rather than sort of trying to model, say, points on a line or some kind of ordered point set, we want to model uh, trees, rooted trees, okay, of some directed graph. Okay, so there's no keys associated with these vertices. There's no order of these points. So instead, this is a data structure that maybe starts with n vertices and no edges, and you have queries that are allowed to add a parent edge or remove a parent edge that forms bigger and bigger trees or breaks up trees into forests. So anytime you're sort of maintaining a forest of rooted trees. Okay? And maybe the kind of query that you want to support uh, in this kind of model, you would, let's say that all the nodes are also associated with weights because that has something to do with your application. You might point to one of these nodes like node X here and say something like, okay, give me the sum of all edge weights, not edge weights, sum of all weights uh, in the subtree rooted at X. Okay, so instead of doing everything between point A and point B, now we're doing give me everything in a subtree rooted at a vertex, this vertex or that vertex. Okay, and of course it doesn't have to be a sum. You can ask for the max value, the min value, or maybe each node is associated with a list. Can you combine all the lists and so forth? Yeah. All right, that's the second one. Now putting together these slides, I realize we probably won't have time for this, but I thought I'd at least introduce it anyway because it's partly what motivates the preceding ones. Okay, this one I thought would be more fun. So we studied, spanning forests are help you decide if two vertices are connected, right? If you build a spanning forest and if you want to know if vertex U and vertex V are connected, you just have to check to see if they're in the same tree in your spanning forest. Okay, so we've done a lot of problems about this kind of thing. Now, in what's called the dynamic graph setting, okay, you want to do this as the graph changes. Okay, so you have some undirected graph, and the user says, let's delete this edge. Like maybe you're modeling a network and you drop a connection. And you want to be able to update your spanning forest. So if you delete an edge that's in your spanning forest, you need to figure out if you can fix it, if you can find a replacement edge uh, to put your forest back together, or if there is no replacement edge, in which case there's nothing to do. Now you can run breadth first search and depth first search to do this, but the question is, can you do this something in like logarithmic time or something? And continue to figure out if 2 points are connected or not in, say, logarithmic time um, as edges are inserted and deleted from your graph. Okay, so it's maybe a different model than you guys have seen before in most basic data structure classes, but it's sort of a natural one. You're sort of taking a basic type of graph problem, and now you're kind of turning into a data structure problem and saying, okay, well, as the graph changes little by little, how long does it take to sort of resolve this or that basic graph problem? Okay. Again, I don't think we'll have time to get to this, but since I made the slide, I thought I'd explain it. Okay, so all of these things, especially the last two, require or make heavy use of an interesting kind of binary search tree, which will be most of our discussion, I think. It's called splay trees. It's another data structure by Bob Tarjan. I sort of decided to present this instead of Fibonacci heaps. Okay. So let me remind you guys about search trees. I know maybe it doesn't need reminding, but as usual, we're storing keys in a tree. Everything in the left subtree should be smaller. Everything in the right subtree should be bigger. And that lets you navigate and find keys in your tree by going left, right, left, right, left, right. You guys have probably done red, black trees and 2, 3 trees or whatever in the past. We did lazy rebuilding um, a couple of weeks ago, which in particular, they all worked very hard to make sure the height of the tree was always log n, or within a factor of log n. That was always the name of the game, because we know really most of these operations take time proportional to the height of the tree. Okay? So the data structure we'll talk about today is quite an unusual one. It's still going to get that log n type of performance, but it's going to be a binary search tree, but it's never going to be balanced. Doesn't even try to be balanced, and it's going to do lots and lots of rotation. So I'm sure one of those trees, like AVL trees, maybe you guys did, but you guys have maybe seen a tree with rotations before. Okay, some of them do. So we'll do it in more depth, but this is really going to like go all in on the whole rotation scheme. And yeah, it's very interesting, and it lets you do a couple kind of more subtle things that some other trees cannot necessarily do, which again is most useful for some of these more sophisticated applications like that rooted tree stuff or the dynamic graph stuff. Okay, but this in itself is already pretty wild and crazy. So hopefully a good example of amortized analysis. So let me explain what I meant by putting rotations on steroids. So the idea is that every time you find an element, every time you even search for an element, you're going to rotate it all the way to the root. Okay, so let's say that we're looking for this key 6. Look at the top tree, somewhere kind of on the left. Okay, and you search 6, or you update the value associated with key 6, whatever. Okay, and what this data structure will do is going to gradually rotate 6 up to the root. Okay, so it's going to first try to, and one sort of curious feature is that it's going to do double rotations or single rotations, but it's always going to try to do a double rotation, so to speak. It's always going to try to take a node and rotate it up 2 levels and kind of rebuild some stuff locally, unless it's only 1 level away from the root, in which case it can only do a 1 rotation anyway. Okay, so here, 6 is going to roughly rotate up 2 levels and should occupy the same slot as 5. And so that's what you see in the second tree, where at some level I basically put 6 up there and just rearrange the tree around it in sort of the most natural way with the minimum number of changes. And then now from 6, you're only 1 spot away from the root, so this would just be a single rotation. You rotate 6 over, and the keys have been adjusted around it. Again, you're not rebuilding the whole tree. You just kind of lift the whole subtree and move it by using pointers. Okay, so that's basically the only rule of this data structure. Every time you sort of touch a key, you rotate it all the way to the top, doing double rotations mostly, except maybe at the end you might do a single rotation. Okay, so it seems like this is possibly a heuristic that some people were using anyway. So what's the intuition? Often in many real cases, the same key gets searched again and again and again and again. There's some kind of heavy hitters type of phenomenon. And so the nice part about this is if you search for 6, 6 is now at the root. So if you search for 6 again, you'll find it right away. And in general, the keys that you search for most often are going to be closer and closer to the root. And so if you do have a lopsided kind of query behavior, then you might hope this does a little bit better because it's biased towards the most frequently searched items. In fact, there's some thing called competitive analysis that can make that discussion a little more formal, but we're not going to do that here. Okay. All right. So, okay. So that's the high level idea. this uh, this operation of taking this vertex you find and rotating it to the root, I'm not 100% sure why, but it's called splaying. So I think today we'll just talk about splaying a particular key that's already in the tree, but you can just as well define things like, oh, splay the biggest key that's smaller than X, splay the smallest key that's bigger than X, and so forth, and you would just do the search and then do the rotation on the way up. Okay. And at some level, all we're really going to do is analyze splay, try to show that splay is fast, and everything else comes for free. All right, so let's talk a little bit about these rotations. So there's a funny nomenclature for them that makes it easier to remember. At some level, we have 6 possible rotations because we're looking at 2 single rotations, kind of from left to right or right to left. And then you have double rotations. We could kind of go like left, right, left, left, right, left, right, right. Rather than left and right, for some reason, we've chosen the name Zig and Zag. So like a Zig Zig might be rotating this vertex up to the root. Zig Zag would be that one. Okay, so um, anyway, so it's called Zig Zig, Zig Zag, Zig and Zag, Zag Zag, so forth. Okay, so we have 6 rotations to analyze, although there's really kind of 3 cases, and then there's a mirror image of those 3. Okay. All right, so let's build some intuition. So the suggestion is that at some level, there's kind of only one natural way, or there are natural ways to try to rebuild um, a tree when doing a rotation. Otherwise, I can never actually memorize exactly the rotation. So if I wanted to put uh, X at the root, where X is in the zig-zig location. So let me, let's pull this over. Okay. So what might we do? So we have to preserve order. Okay, so maybe X would go here. I would have to make Z the left child, something like this maybe. Okay, so I think this is preserving the order correctly. So, take for example this subtree that I've called B. That should be kind of all the keys are bigger than X but smaller than Y, and that holds true. I think, the subtree C, that was bigger than Y and smaller than Z. So that's sort of the natural place to put it. Okay. So, so that would be Zig Zig then. I never quite remember exactly what it does, but I usually just put the right node in the root and then build it around it. There's usually one natural way to do it. Okay. I can let you guys try Zig Zag. So here you would want to put, you would want to put X in this picture at the root. I'm not 100% sure how the best way to turn this into a picture, so maybe just shout out suggestions of where to place what. I wanted to make X the root and preserve the order. Sure.
Would Y and Z be on either side?
Yeah, Y and Z need to be on the opposite side. Oh no, wait, X is, well, Y is smaller, right? Okay, is that what, did you mean like this? Okay, let's put Z there. Okay.
A to the left of y,
A to the left of y. Okay.
B to the right of y,
B to the right of y.
and then the same thing for z, but C.
Okay. It seems like every time I don't have to create any new edges, we have just enough. I don't really know why that is. If that's a provable thing or just a coincidence. Okay. So there we've done a zigzag rotation, and we sort of rebuilt the tree around X. Keep in mind this might be just part of a much bigger tree, right? So this is connected to something else. In this one, you can see a little bit of the intuition, although it's a little bit misleading because we don't know how big A, B, C, and D is. But at some level, the picture on the right looks a little bit more balanced than the picture on the left. Okay. Um, I don't know if this is boring yet, but I left one more blank. Um, Zig is just rotating one vertex up. So this would only kind of happen close to the root. So if I first put X at the root, how might I decorate everything around that? Yeah.
A would be to the left of x,
Okay.
y would be to the right, c would be to the right of y, and then b would be to the left.
Okay. B would be to the left of Y. Okay. So again, from what I can tell, with each of these sort of rotation directives, there's really only one way to rebuild the tree. Um, okay. So uh, there's three symmetric cases. Zag Zig is just a mirror image of Zig Zag in a sense. Zag Zag is a mirror image of Zig Zig. And then Zag will be a mirror image of Zig. So here would then be 6 rotations, I believe. All right. So okay, so this is sort of a very curious data structure though. So each time, if you're trying to search for a key, you you find it down here, and then you start doing these rotations back up to the root, right? And it's a lot of rotations. I mean, each rotation sort of takes constant time because you're manipulating like 6 or 7 pointers or something. But the path to that node could of course be very long, right? So this tree is like it's never necessarily balanced, right? There's no particular attention paid to the height or paid to the sizes of the subtrees or anything like that. Um, and there's no explicit effort to balance. And it's easily going to take constant time in the worst, or linear time in the worst case, if you have to do a lot of rotations up a tree, right? So uh, there's no clear reason why this tree should behave like 2-3 trees or red-black trees or lazy rebuilding, which are so clearly more directly trying to maintain a log n height tree. Okay, so finally here comes some amortized analysis. So we're going to try to analyze this thing with a potential method. Okay, and I think this will sort of put the potential method a little bit on steroids. Okay. All right, so yeah, I should mention the authors, Tarjan and Sleater. We've seen Tarjan many times before. Okay, I don't know how they came up with this, but they did. Okay, so we're going to define the potential of a tree to be the logarithm summing over all the subtrees of the tree, the size of the subtree. So maybe a better way to look at it is, I can think of each node in the tree as representative for its subtree. And instead, I'm going to sort of define a potential for every key, and I'll sum them up. So a slightly different notation that I find more convenient is to define for every vertex or key its own potential function, which is, again, the log of the size of the subtree rooted at x, okay? Which means the overall potential will be summing over all the keys, all the individual potentials. Okay, so you're summing up over all the subtrees the log of the size of the subtree. Okay, at this stage it should be completely mysterious why this would work. Yeah.
Wouldn't summing all the potential x's double count a lot of sizes?
Yeah. Absolutely, absolutely. So if it was a balanced tree, you have log n at the top plus 2 log n over 2s plus 4 log n over 4s. Yeah, so you're double counting a lot, although they are wrapped in a log, which is diminishing a lot of stuff as well. So in fact, let me give you two examples. So in the unbalanced case, I'll do unbalanced first. The sizes go n, n minus 1, n minus 2, n minus 3, and you're going to get roughly n log n because you'll have at least n over 2 terms of size, log n over 2. Okay? In the balanced case, okay, this takes a little bit more effort to crunch out, but a balanced tree will have potential big O of n, where on average, each vertex is contributing a constant. Okay, so this gives a little bit more intuition for the potential, because we can kind of see that for us, the worst case is always a very unbalanced tree, and that has this very large potential of n log n. And for us, a good thing is always a potential of size n. I mean, a balanced tree, and the balanced tree has this potential of n. Okay, so at least at these extreme points, the tree with smaller, with better balance, has a smaller potential. Okay. All right. Okay, so that's okay. So what we want to do is for each of the 6 rotations, and what I'm actually going to do is focus on one, suggest that the other 2 are similar, and send you to the notes. Um, uh, but for each of the rotations, we're going to analyze, each rotation takes constant time. We know that. But we'll analyze how the potential, this crazy sum of logs, changes as I do just one rotation. And the bounds we'll get will have a particularly nice form where when you add up all the rotations over the course of one of these splays, we'll be able to do something with it. Okay, but the grungiest part of the analysis is just focusing on one rotation at a time. Okay, actually, the rest comes together much more cleanly. Okay. All right, so where do we start? So one observation uh, that turns out to be pretty valuable is that what is the maximum that a single vertex's potential could be? So one of these potential of x's, what's the biggest it could be? Yeah, log n. Okay, so this doesn't seem like a big deal, but it is going to be very useful actually. So one piece of information is that the maximum of any one of these potentials is log n. So also any potential can change by at most log n. Fine. But if I can get a running time, some kind of bound where I can show that, I don't know, the running time I spend plus the change of total potential. Let's say I'm splaying X right now, right? I do one rotation at a time. If I can show that the running time plus the total change of potential is at most the change in the potential of X, okay, then I can rely on the fact that the potential of X is also bounded above by log n and get a log n amortized time. So this will be made a little bit more clear in a second, but I'm just trying to foreshadow. What we're going to try to do is show that as the potential changes, the potential maybe goes up, right? It started a balanced tree, and you do a lot of rotations, and that makes you a little unbalanced. But if the potential goes up, we're going to try to argue that the potential of the node you're splaying also goes up by a little bit to make up for it. Okay, so if the total potential goes up, which again, the total potential accounts for all the nodes, we're going to try to show that, I don't know, it's at most, say, 5 times the increase in potential of just X. Okay, and at the end, we'll still be able to say the potential of just X is at most log n, and then we'll get that log n amortized bound. Okay, so I think this is a bit more, it's still a potential function method. It's not introducing anything kind of technically new, but I think this is quite more clever than anything we've done. Okay, so all right, so that's one observation. I'll kick in later. All right, so let's look at, I'm going to focus on just one rotation. I know it involves some calculations, and I think you won't mind if I skip the last two once we're done with it. So let's look in particular, I guess, at Zig Zag. Okay, so the claim for Zig Zag is that, you know, roughly 2 plus 2 accounts for the rotation time as well, the actual time to do the rotation. The change in total potential, okay, we're going to try to argue is at most 3 times the change in potential of just X. Okay, so that's the bound we're going for. So again, total potential is the sum of all the log of sizes. And for X, that's just a log of the size of its own subtree. Okay. And you know this is probably going to go up. Well, yeah, this is going to go up, right? Because you're going to make this the root and everything else is going to become a subtree. So the size will get a little bit bigger. So that will be positive. But the important thing is to be able to charge the total change in potential to the change in potential just of X, because we know all those changes for X can only add up to log n at the end. And it might be, okay, it might seem intimidating to try to handle all of the total potential, right? Because it's a sum of many logs. But when we do one of these rotations, many trees stay the same. So if I look at that subtree here, I'm going to move some things around it. I'm going to move the relation of that tree to others, right? It's going to have different parents. But that subtree itself won't change, and all the subtrees will stay the same inside of that. You know, this kind of subtree as well will not change at all. Okay, it's going to get rearranged. But that subtree and everything inside of it is not going to change. Okay, and you know, whatever is the rest of the tree out here, that's also going to get rearranged. But it's going to have a new child when all is said and done, because X is going to hang off of the rest of that tree. But none of the cardinalities are going to change for any of those nodes. So in fact, the number of kind of moving parts is a little bit more limited than everything changing, which will help us. Okay, so here then is sort of the simplifying thing where I remove the parts that don't change. Okay, so I'm going to let A also denote the number of vertices, the size of the subtree labeled A in that picture, the size of the subtree B labeled in that picture, and so forth. Okay, and try to prove this claim that the total potential change is going to be bounded by the change in potential of x. This will be the most technical part, and then we'll be able to back out, and hopefully the big picture will be more fun again. Okay. We also make sure I do the calculations correct because it does get a little detailed. Okay. All right. Okay. So, all right. So now here then is sort of all the data for us. We're doing a zigzag. I'm moving x to the root. We rearrange the tree on the right. Again, just to remind us, the potential is the log of the size of the subtree, and the total potential is the sum over all the nodes. Okay. Now, if I look at, well, okay, so the first thing is just to write down what is the change in total potential and what is the change in the potential of x. So we can say start with the change of potential of x, because that's a little simpler. That's only one node. So, afterwards, x will have potential that's like log of, we have one for x, one for y, one for z, and then a plus b plus c plus d, right? So we should get 3. Okay. That would be the potential of x afterwards. And before, you have log of 1 plus b plus c. Okay, so x itself sort of added on, it added y, it added z, it added subtree a, and it added subtree d. And so that's the difference. Okay. All right, so that one has less moving parts. So, okay, what about the change in total potential? So which of these trees even at some level change? Okay. What's the best way? Okay, so of course the trees A, B, C, D and themselves don't change, so I don't have to worry about those potentials. I can just rattle off the potentials of X, Y, Z afterwards and X, Y, Z before. Subtract them out, we'll have one thing that cancels out. So, okay, so the log of the change of potential, total potential might be something like, first for X, you'd have log of 3 plus A plus B plus C plus D. Actually, let me do it like this. So this is for X. But before, it was log of 1 plus A, plus B plus C. Okay, so that would be X's contribution to the change in total potential. That's just for X. Y would look like, I guess, log of 1 plus A plus B. But it used to be bigger. So the subtree at Y got actually smaller. Okay, so that's the contribution of Y. Okay. And then for Z, you'd have log of 1 plus C plus D afterwards. And it used to be log of everything, 3 plus A plus B plus C plus D. Okay, so I kind of ran out of space to write, but maybe you guys recognize that these two terms are the same because that just represents log of all the nodes at play in this picture. So those two will cancel out. Okay. So we're really left with log of 1 plus A plus B plus log of 1 plus C plus D minus log of 1. Okay. All right, but all I've done is look at what are the parts that actually change. It's really only the nodes, the subtrees rooted X, Y, Z, and wrote out the difference for each and canceled out one pair of terms. Okay, so Okay, so the first thing we're going to do is we're going to look at, this part will be a little bit analytical, so we'll back out in a moment, but I should at least do the calculations once. Okay. So this is maybe the one part that's hard to guess, is how to deal with log of 1 plus a plus b, and log of 1 plus c and d. Okay. And here we're going to use the fact that log is a concave function. Okay. So just to remind ourselves, a concave function is anything sloped over like that. So if I take two values and I draw a line through them, the part in between will lie underneath the curve, which is, this represents the average value of those 2 points, right? And then this would represent the actual value of the average input. Okay, so this says, concave says that the value of the midpoint is always bigger than the average of the values. Okay, so we're going to use that. I think that's probably the toughest part. So, okay, so the average value is less than the value of the midpoint. So log of 1 plus a plus b plus, there's a divided by 2 that I've moved to the other side. Okay. Right? And we can take out the divided by 2. Should be a leading 2. Okay. But what's nice, right, is I'm trying to figure out how to relate the change in total potential to the change in potential of just x. And I use a different color. This term, I'm missing, sorry, 2 plus. Okay. This term is actually less than equal to this term up here. Okay, sorry, no one wants to watch me write these expressions. Okay, so that's one step, is at some level we figured out how to charge off those two terms towards two of those terms. Okay. What did I think I prepared something? Okay, good. All right, so rearranging, we've shown that 2 plus log of 1 plus a plus b is less than equal to this thing. But somewhere in there we use concavity once. Okay. All right, so let's put everything together then. So the change in total potential is up at the top. The potential of x is that second line. And I want to relate, I also want to say blue is less than or equal to red. Okay. So, sorry. I think I pre-wrote this, so you don't have to watch me write. I don't know if that counts as cheating, but okay. So here I've just plugged in for total potential, the value we calculated, which again is messy, but I guess the only point I want to make that we sort of did it in a straightforward fashion. Looks like I've just dropped the 2 plus a, the negative 2 plus a plus b plus c term, but I'm doing less than or equal to, so that's okay. And now we can use that quick concavity calculation and replace the yellow with the green. Okay. Uh, and voila, I guess we're done. Except I feel like I cheated a little bit. Okay, I did cheat. Okay. I'm not sure if anyone's too concerned, uh, but if I hadn't left out this one term that I dropped earlier and brought it along with me, log of 2 plus a plus b plus c is at least log of 1 plus b plus c, so we can replace it and we get 2 times the potential of x. Okay, I can tell everyone's super excited. Okay, anyway, so the point is that you sort of look at it, you mess around with it a little bit, and I think overall though the message is that somehow I'm able to charge with some analysis that the increase in total potential, while it might have gone up and that would be bad, if it did go up by a lot, that means the potential of x also went up by a lot. So I'm able to relate the change in total potential to the change in potential of just x. Okay. And I guess the biggest takeaway is, okay, you have to take out some paper, do some calculations, and you do need to take advantage of concavity of log. That's actually one reason why we use log as opposed to some other mysterious function. Okay. Okay. So that's how you would do the calculations for Zig Zag. Zag Zig is a mirror image, and you would find yourself basically doing the same thing for Zag Zig. And the other two operations, you would do a similar game, and my guess is that you wouldn't want me to do it. So I guess Zig Zig turns out to be much more complicated to do than Zig. Maybe that makes sense because one's a double rotation and the other one's a single rotation. Um, But we do the same thing where we sort of look at what are the moving parts that actually change, take our time. Somewhere in there we invoke concavity and do a little bit of mathematical cleverness, um, but we're able to establish a similar kind of bound. Okay, so let me summarize. You get bounds like this. This probably makes your eyeballs bleed. So here's a simpler one. Okay, so sort of just rounding up some of the constants. So if you looked, and a simpler version is to say, okay, a single rotation, the increase in total potential is at most 3 times the change of potential of the vertex you're displaying. And for a double rotation, 2 plus the change in total potential from that double rotation is at most 3 times the potential, change of potential just of this vertex. Okay. All right, now let's bring it all together. This part will at least be a little bit quicker. All right, so the running time is basically proportional to number of rotations. Okay, so if I can upper bound 2 times the total number of rotations plus the total change in potential, that would give me an amortized running time. Okay. So now, as you display x to the top, you do a bunch of rotations, and for every rotation, except for maybe the last one, uh, kind of individually, piecewise, the change of potential is going to be bounded above by the change of potential of this particular key that you're making into the root. So that should give you, I guess, 1 plus because of the last one, but 3 times the change in total potential of x. Okay. And of course, since each x has non-negative potential, the total increase is at most the final potential. Um, which at long last is at most log n. Okay, so somehow this analysis is very clever. It's able to look at these individual rotations and argue that the change in total potential can be charged to the change in potential just of x, and x itself has limited maximum potential. Okay. All right, so okay, so that should give us log n amortized time for each display. Okay. All right. Okay. So that's where log n type of bounds come in. And then you can figure out how to do insertions and deletions. Because insertions, you just put it at the leaf and then you splay it back to the top, and that'll give you log n time. All right, so I wanted to talk a little bit about how to use these splay trees for range queries. So let me remind you. So the general setting is you have a bunch of keys that are orderable. They have, say, weights, and you want to find the sum of weights between any two keys. You want to be able to update this quickly. You guys probably know how to do this in the old-fashioned trees, but it's fun to think about how to do it in splay trees. Okay. So we'll assume that the keys are in the tree, and they carve out some kind of path in our search tree, in our splay tree. And we want to quickly sum up all the values with the keys in the range AB. Okay. All right. So let's see. Okay. So I think the first part might come naturally from the usual trees, but the first thing you might try to do is for every node, you can try to maintain the sum of all the values in the subtree rooted at that node. Right? We did something similar for lazy, or briefly mentioned something similar for lazy rebuilding trees and so on and so forth. But the only problem is that in those balanced height search trees, we can carve out a path of height log n, right? And then we just add in log n numbers. But with splay trees, you don't have a balanced tree, right? So you can have very long paths. So you don't just add up log n number. Like that's not strong enough to pull off the argument. Okay, so we're going to do this first step similarly, where we maintain a sum for every subtree, but and you can adjust your rotation. So if you do a zig, you have to update a few sums, but that's pretty easy by looking at the numbers nearby. But the problem now is how do I actually get the sum between, say, 2 points A and B in the tree? And you can do something cute with this splay tree. So I was going to give you guys a chance to guess. Does the question make sense? Some level? How can I use a splay tree to answer this range query, even though the path might be very long? You're only going for amortized time. Yeah.
Could you potentially either rotate one of the endpoints to the root or use the root of their path and use that sub there?
Yeah. So that's definitely on the right path. So you're going to want to update and kind of change your tree, and you're going to want to sort of rotate at some level A and B. Okay, that would sort of be the first part of the sentence, I guess. So you want to do something with A and B to sort of make the rest of the computation convenient. Yeah.
If you could get A and B to be the two children of some parent, then everything between.
Okay, great. So if I had like A and B kind of right next to each other and sort of everyone will be sandwiched in between. Okay, now how can I do that?
Rotations.
Yeah, okay. How do I do that with just splay? So splay would just take a node and rotate it to the top.
Rotate A to the top, and then rotate the.
Okay. So we can try to splay A first and then splay B. Okay. So if I splayed A first, then B will be somewhere down here, and there'll be something else here, right? And then if I splay B after that, A will come down, and I'll have something like that. And all the time, as you do rotation, you update a few local sums. So you still have all these pre-computed subtree sums. Okay. So in particular, right, down here in this subtree, I have all the keys that are strictly between A and B. So now I just have to add whatever the weight of A, the weight of B, and the weight at the root, that pre-computed sum at the root of that subtree. Okay, so you can use splay to very easily rearrange the tree in a way that's convenient and only pay log and amortized time. That's really important for those sophisticated applications I mentioned at the beginning that we probably don't have time for at this rate. Okay. Okay, so in that way you can get log and amortized time. Um, okay, so this question is a little bit trickier, um, but maybe I can open up the floor to give you guys a try. All right, so range queries, where you're concatenating lists, but the hard part is that, okay, so every key is associated with a list of stuff. And I want to say, give me the combined list of everything with key between A and B. Okay. And the only reason this is actually really hard, if every element had a non-empty list, then you actually kind of have time to visit every one because you have to glue together the lists anyway. But the issue is that maybe many of the keys have empty lists, right? And you want to kind of skip it, so to speak, right? If like if that whole thing was empty, if everything was empty, I don't want to traverse the whole tree to find out it's empty. Okay? So the goal is to get some kind of running time that's proportional to the number of elements I output. Okay? All right, any ideas for this? Yeah. Oh, okay, so try to store maybe at each, if I could just store at this root or something, if that was actually a root of a whole subtree, all the lists combined. So I think the only thing that makes that, you can do it in a clever way with something called kind of like lazy building lists. But the only thing is that when you do a rotation and you update some of these lists, you want it to be sort of a constant time operation. So we didn't do that in detail, but implicitly in the last application, when I did a rotation, I would update some of those sums. But I just have to look at a few numbers nearby to do that. Now, with the linked list, oh, you can be very clever and possibly do that, but at least a straightforward one, you'd have some issues rebuilding the list very fast. I guess it's possible there's a doubly linked list if you keep track of what comes first, what comes last, or something like this. But um, let me give maybe an alternative. Um, so, so one thing you can do, this is actually not the best way, but it's the easiest way to explain, is you can maintain a counter at each subtree of what's all the sizes of the subtrees. Um, what's the combined size of all the lists under that subtree? Okay, so in particular, you'll be able to figure out if a subtree has nothing at all. Okay. Now, okay, how can I try to use that? Okay, so I might first splay A to the top if I want to get all the combined lists between A and B. Okay, so I would splay A to the top. I have some other tree here. Okay. And okay, maybe A has some value, so that forms the first part of my list. So I first, print out those three. Fine. But now I need to move on to the next key that's sort of non-empty, so to speak. Right? So I want to find the next key after A that has at least one value in the list. Okay? So from this kind of situation, maybe there's the next key is somewhere down here, B is way off over here, and this has a list of elements. Okay? All right, so maybe in this diagram, X is the next node that has a non-empty list associated with it. And just by knowing, just having these counters of, in particular, knowing which lists are empty and non-empty, I would be able to do a search. Okay, I know this is non-empty, and I would be able to find my way over and find that first key, X in this case, that has a non-empty list. I guess rather than the count, I probably could have just stored a flag saying, is there or is there not any elements in this subtree? Okay. But having this information would give you enough to sort of find that next key X. And then once you find that next key X, then we can use the same trick as before. Okay, so the only painful part is, okay, well, that red zigzaggy path may be very long. How do I count for it? Well, I'll splay X to the top. Okay, so the time I took to find X is proportional to the real time spent splaying X to the top, and splaying takes log n amortized time. Okay, so for each subsequent key, I just have to find the key, and then I call splay, which even though I spent much longer than log n time, still counts as log n amortized time. Okay. So I would splay that next key to the top, and I would keep going in this fashion where I keep sort of finding the next key with a non-empty list, splaying it to the top, paying log n. Okay. And you would get like k times log n would be a worst case bound, where k is sort of the total size of your output list. Okay. K would really be the number of keys with a non-empty list. Okay, I think you can get k plus log n was an idea similar to what was suggested, but I think that's a little bit harder to describe. Okay, all right, so much for splay trees. I don't know, the title fun was trees wasn't meant to be ironic, but maybe at this point it is. Okay, let me briefly try to describe how to use splay trees for this somewhat more complicated, I don't know if it's complicated, but it should be much more different of an application than what you guys have already seen, because I think the previous stuff is similar to the binary search tree type of stuff that you may have seen before in your data structures class. So this problem is this sort of dynamic tree model where you're trying to maintain a forest and be able to do subtree queries. So you're adding and deleting parent edges, and maybe the nodes are associated with values, and I want to say, give me the sum of values associated with the subtree rooted at a node X. So, okay, so the main operations to manipulate a forest, um, uh, again, they're called link and cut. Okay, so link is adding a parent edge. So one of those vertices needs to be the root of its own tree right now. And then you choose some other vertex W, and then you'll make that kind of tree rooted at V a subtree and a subchild of W. Okay. Cut will delete the parent edge of the vertex. Okay, so you can add and remove these parent edges, and over time you update your rooted tree. Okay. Uh, Besides that, other operations include what is the root of my tree? I give you a vertex, it's sitting in a forest. Return the root of the tree. That'll let you identify if two vertices are in the same tree. There's also one called reroute that we won't need today, which kind of rearranges the edges to make a different vertex, the root of its own tree. Okay, so that's this dynamic tree model, is that you're adding and removing parent edges, and you want to still support subtree queries. Okay, and here then is I'll just get to the point then. Okay, so this is going to use this clever idea. So did you guys talk about Euler tours in like discrete math before? Okay, so you might know that an even degree graph, you can kind of go in and out, and traverse all the edges. I guess this is also sort of like an in-order tree. Well, no, well, okay, it's not necessarily a binary tree. So let me draw this out from scratch. So if I started from R and I started crawling around this tree, right, and I go down and up and down and up, you might notice that I end up visiting every single edge once in each direction. So each edge got visited on the way down, each edge got visited on the way up. Okay, so that is just one possible Euler tour. I could have gone in the opposite direction. You can choose any order of subtrees you wanted. I chose one that's easier to draw. Okay, and the idea is, imagine that as I did this, starting from the root, I listed the names of all the vertices that I visited, right? So I started at the root, so I printed R, then we went A, then B, then back up to A, then C, back up to R. Okay, so that's what this list is giving. So think of this list, visit into Euler tour. Okay, so here then is going to be our big trick for the subtree problem, is I'm going to use the Euler tour as giving me some kind of ordering of sort of symbols, where each symbol represents when the vertex was visited on the tour. And we'll build a search tree, like in particular for us, a splay tree, uh, over this list. Okay, so what does that let us do? Okay, so what I want to do then is, now for a particular vertex on the Euler tour, uh, if you look at R, for example, R appears like 3 times, the root, because it appears at the very beginning, at the very end, and we revisit it at some point in the middle when we switch from one subtree to another. Okay. But I'm going to let, for a particular vertex V, I'll let V minus denote the first time it appears in the list, and V plus denote the last time it appears in the list. Okay. And, sorry. Okay, so, what's the point of all this? Okay, what's really nice about this Euler tour, and really the whole point of it, is that once I maintain sort of all of these visits in the Euler tour in, its, for example, a splay tree, okay, and if I, at some level, if I wanted to look at, for example, the subtree rooted at A, okay, so if I wanted to look at the subtree rooted at A in the Euler tour, that's sort of, the Euler tour visits A and it goes through the whole subtree before it backs out from A. Okay. So as a result, all of the vertices in that subtree are getting mapped to an interval on that list of vertices in the Euler tour. In particular, the interval between A minus and A plus, because A minus is where I entered the tree rooted at A, and A plus is the tree when I left the subtree rooted at A. All right. So why is that now useful? Is that by doing this Euler tour trick, if I wanted to add up all the values, if I had values associated with vertices, I wanted to add up all the values at a tree rooted at V or something like that, I would be looking at the Euler tour and I would be adding up all the values in that interval of the Euler tour. So maybe if a value is associated with V, I'll stick it onto V minus or I'll stick it onto V plus. It doesn't matter as long as you're consistent. Okay. And so the whole point of this Euler tour trick is now I can take my subtree queries and turn them into range queries like we just did on splay trees. Okay, because now I'm looking at the sum of values between 2 points on a line instead of trying to get the sum of values inside of a subtree, which a priori seem difficult. Okay. All right, let me try to finish. Okay, if you wanted to do those link cut operations and you wanted to actually make this like the tree is changing and you're adding and deleting edges, then all you have to do is figure out how to update the Euler tour. Okay. So, for example, if I wanted to take the subtree rooted at V and make it a child of U, then in terms of the Euler's tour, I'm trying to figure out how to insert sort of that Euler's tour from V subtree into, the Euler's tour up above. Okay. But in that case, I would say figure out where I entered U plus. And so here you kind of see it being inserted in between. Okay. So actually, it should probably be, I feel like the U plus should have been here. Okay. But you do a little bit of surgery uh, uh, to insert it. Uh, and I guess the main takeaway, you probably don't have too much time to do it slowly, but if you're using a splay tree to maintain the Euler tour, then you can play games with a splay operation to make it work. So uh, again, whether or not U plus goes before or after might be an issue here, but oh no, U plus is when you leave U, so that's why it's coming before U plus, so that's okay. U minus is when you enter U. Um, but if you wanted to do that kind of surgery, you can splay U plus to the root, V plus to the root, and then once you have this kind of arrangement, it's easy to make V plus the left child of U plus and rearrange those subtrees. So one subtree here goes to one subtree there, and so forth. Okay, so again, I'm not doing a great job because of time constraints of kind of building up the drama and the interest, but uh, I think that what's kind of going on is you have this creative reduction from doing subtree queries to range queries over the Euler tour. Uh, but then to make this thing dynamic as the things update, you have to do some surgery to your binary search tree. And this is another kind of creative use of splay, is that those nodes that you're really interested in the representation, you can splay to the top and figure out how to rearrange things when they're at the root. Cut would be something similar. Cut means you're taking something out of the Euler tree because you're deleting a parent edge. Again, you would do some clever stuff to reduce it to some splay operations. Okay, so all right, not a great presentation, but that's okay. Okay, I'll just finish there, and I'll just say that uh, okay, so that's just one example of splay trees doing something slightly extended and going slightly beyond what you might have normally seen from binary search trees before. So just quickly, I wanted to ask, I didn't have anything particularly planned for Tuesday. I was just going to load up word problems with nice pictures. Would you guys like that, or do you want? Okay, I'm seeing lots of nods, so we'll just do that. We'll just have review. There's no